All right, guys, a couple things on Google Classroom. Yesterday I added a link for the recorded Zoom videos for this class because I'm going to keep them separate from multi. So I added a link for that, and then I also added answers to the problem set. So if you haven't yet seen the problem sets, they're a lot different than what they look like in multivariable, where they were a textbook, problems out of a textbook. This one, I've taken them and I've typed them in because we don't really have a specific textbook. So I took the problems and typed them in. So it's more just like a sheet with all the problems on it, which means you don't have that handy little link that you can click to see the answers. So I posted answers so you guys can check and see if you missed any problems or anything like that. And then at that point, you should ask questions, ask me, ask a friend, whatever, to try and figure out what went wrong. I'll post the full worked out solutions later, like after the problem sets. I don't really want you copying those. So the answers are literally the answers, with some of them giving a couple hints of like where you might want to go in terms of your work, but I'm not posting full worked out solutions because I don't want you to just copy my full worked out solutions. So I posted answers. You guys can ask questions and things if you're not getting the correct answer or not understanding where the answer is coming from. Those things are now in Google Classroom as well for you guys. Otherwise, we're going to keep going today. We still have some review stuff left in today's, and then we're going to start looking at some matrix stuff, but we're still not even really solving any of the matrix things yet. We're just going to kind of look at setting it up today. All right, so we're going to start by looking at planes, which that part's definitely a review from last semester. We already saw planes, equations of planes and stuff like that. Although even up to the final, some people could not get the equation of a plane. So planes, the reason we'll look at planes also is as we start to talk about our systems of equations. With a two-dimensional system of equations, you can picture it as lines, trying to find intersections of lines. In 3 dimensions, it would be planes. And a lot of our examples will be 2 and 3 dimensions, so you can kind of try and picture that situation. Once you move past 3 dimensions, we sometimes still even refer to them as planes, but they're not, obviously you're not visualizing a 5-dimensional plane. Not going to happen. So with planes, we need 2 things to come up with an equation for a plane. Again, this is review from last semester. We already did this. One, you want a normal vector, meaning perpendicular to the plane. So n, normal to the plane, perpendicular to the plane. And then we basically just need any vector in the plane or parallel to the plane. With that, we usually think of 2 different points on the plane, x naught, y naught, z naught, a specific point on the plane, 1, 1, 1, 1, 2, 3, whatever, some point that's on the plane. And then x, y, z representing any other point on the plane. Okay, like when we have an equation that has an x, a y, and a z in it, that's the points on a parabola or the points on a line. This one is the points on the plane, x, y, and z. So remember, if we have 2 points, we can come up with a vector in between by just subtracting. Okay, so vector v here would represent a point parallel to the plane, or a point in the, a vector in the plane, or a vector parallel to the plane. N would be normal to the plane. And so when we take the dot product, that's where we get our equation, a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Okay, and so that's usually the form we used last semester, because last semester we were mostly concerned with like, this is a plane, this is the tangent plane or whatever. With linear algebra, we're usually looking at planes in terms of solving a system of equations. So we'll usually have solved this down by distributing the A, B, and C, and then gathering up the constants on the other side. Okay, when we go to solve a system of equations, this is a scalar that we usually just call D. We'll add them all together, distribute the A, the B, and the C, add up all the stuff we can. And then when we're solving our systems, we usually leave the variables on one side and everything that doesn't have a variable in it on the other side of the equation. And so that's where we'll kind of usually have our planes. It's still the same general idea of where we're getting this thing from. It's just in multi, we didn't really care about what form it was in because we could do the calculus in either one. Here, solving a system, we usually want it in this form. This really shouldn't be an equal sign. So we'll usually use this form ax plus by plus cz equals d. As our plane equation. And really, this is still a linear equation. This is a three-dimensional linear equation. It's not a line. Linear refers to the powers of the variables being 1. Okay, that you're not having x squared or y squared or z squared or x times y or y times z or whatever. Linear equation just means all of our variables to the first power. So you can have a 10-dimensional linear equation that's just a bunch of variables all to the first power. Okay, so this plane is our third three-dimensional linear equation, but you can keep adding variables, still linear, as long as you're not multiplying variables together. Okay, so planes can also be described as a linear combination of vectors. In general, we're not solving things this way, but this idea comes up over and over and over again in different concepts. So we're going to keep practicing picturing things, visualizing things as linear combinations of vectors. So we could describe all the points in a plane as a linear combination of vectors. There are infinitely many choices. Okay, so the method that I'm using here is not the only way, it's not the only answer. But this is kind of the way I usually think about how to do this. And that's what a lot of linear algebra is like you have a method that you're trying to make that will work in all situations rather than just kind of like a guess and check and a pick a random thing method. You're trying to come up with a way that would work every time. So what I usually do is I take my plane and I solve for one of the variables. Okay, so like here you could get x equals y plus 3z. It doesn't matter. You could have solved for y or solved for z. I would just pick something that's easy and do that. Okay, and then I'm going to kind of think of this as if I had an equation where x was the dependent variable and y and z are my independent variables, right? I could plug in y's and z's and generate x's that are also on the plane. And this is the reason I use this is very similar to something we'll do later. Oops, not x, sorry. So I'm just going to plug in some y's and z's. Easy ones like y equals 1 and z equals 0. Okay, I don't want to plug in 0 and 0 because then I'll just get 0, right? This plane does go through the origin. So I'm going to pick something easy like 1 and 0. When y is 1 and z is 0, notice that x will also be 1. Right, if I just plug them into that equation. So notice the point 1, 1, 0 is on the plane. The point 0, 0, 0 is also on the plane, which means we have a vector 1, 1, 0 parallel to the plane. Okay, or you could think of it as being on the plane if you wanted to. If it was from the origin out to 1, 1, 0, the plane also goes through the origin and 1, 1, 0. So that would be parallel. Okay, and then I usually let y be 0 and z be 1. Okay, again, those variables I'm picking as zeros and ones because those are the two variables that are on the right-hand side of the equation that I solved the plane for. It doesn't have to be always y and z. It's just the two kind of independent variables in the situation that I've kind of created. So when I plug in y equals 0 and z equals 1, notice that I'll get x equals 3. Okay, just plugging into the equation y equals 0, z equals 1, I get x equals 3. Again, that means the point 3, 0, 1 is on the plane. The point 0, 0, 1 is on the plane, which means the vector 3, 0, 1 is on the plane. My goal here is to get, I wanted two vectors to describe the plane. Okay, why I need two, we'll think about like we can describe the entire XY plane, the plane we're used to in algebra, with I and J. Well, I and J, right? With those two vectors, we can describe anything on the plane that we want as some multiple of I plus some multiple of J. Here I just need two. Any plane, you really just, well, any plane through the origin, you just need two. So this is the way I usually come up with my two. I want them not to be multiples of each other, because if they're on top of each other, that's not good. I just need them to be two different, what we call independent vectors. And so this is usually how I come up with mine. Now, if I take any multiple of 1, 1, 0, plus any multiple of 3, 0, 1, I can get any other vector in the plane. Okay, the reason I use y and z as my multiples is because I let y be 1 in that first one and I let z be 1 in that second one. So that's where I'm getting these from. Technically, it could be any letter. We're talking about any multiple here. So it's not incorrect to use other letters there. The reason I kind of like this method is if we actually multiply this out, notice that I'll get y plus 3z in the x spot, which is good. I'll get y in the y spot and z in the z spot. So basically, y and z can be anything, and x will be y plus 3z. The plane goes through the origin, which literally just means we're pointing at different locations on the plane from the origin. Okay, so this is my answer here. Is I could take combinations of those vectors, those two vectors in the plane, and I could get any other vector in the plane. Kind of like I can take combinations of I and J, our standard unit vectors, in the XY plane. Only this is not the XY plane. Okay, this is a different one. Okay, and so I can describe the plane, all the vectors in the plane with combinations of these two. Again, there are infinitely many choices. You don't have to choose these two. You could choose any two independent vectors in the plane and it would also work. Okay, this is just how I typically come up with mine. If it doesn't go through the origin, that causes a problem with this method. Okay, so this plane doesn't go through the origin. It's parallel to the other one, right? The coefficients are the same, so it's parallel. But now it equals 2, not 0, which means the point 0, 0, 0 is not on the plane. The method there won't work unless we add a step. So first, I would solve as if x minus y minus 3z equals 0. And then we'll just shift it because it's just a shift of that plane. That plane, it's parallel to that plane to have the 2 there instead of the 0. So we would do the exact same thing. And that'll give us all the vectors in the original plane where d is 0. And all we have to do is shift it by adding a constant vector. Okay, so if our plane doesn't go through the origin, we actually need a third one to kind of shift it. The reason that I pick it in the x spot is because when I solved for x. So the way I came up with those two is by solving for x. That's why I picked here. If I did it by solving for y or for z, I would put the 2 in that location. So again, there's other choices that could happen here. If you had solved for y instead and kind of come up with it that way, you'd have added the 2 in the y location of the vector instead of in the x location. And that's because we don't have points. We can't find our vectors by subtracting 0 to get our vector, because our plane doesn't go through 0. So we kind of have to shift all the vectors away. Okay, and again, we're not really going to solve anything with this at this point. You're just trying to kind of picture this idea of expressing things as linear combinations, because later that'll kind of come into play in a bigger way.
Hola.
Okay.
What's up, Drew?
Ian, you're not muted.
Oh,
Is he playing a game or something? All right.
no, I'm looking for a link.
All right. So we have, and I forgot to change several of these things. I thought I did that. All right. In a matrix, this is review algebra 2. So it's been a while for you guys seeing a matrix. And then you also only probably did it for a little while. You guys did a few things with matrices. So we have matrices. We usually describe them as M by N, meaning rows by columns. So when we say like 5 by 4, 5 rows, 4 columns. Okay, so usually the first number is rows, the second number is columns. And then we just label each element with a lowercase letter and a little subscript that tells us what row and column we're in. So like Aij would refer to the element in row I, column J, so that if you have a big matrix and you just want to refer to one element, you could be like A57. And what you're talking about is the element in row 5, column 7. So you could go to row 5, column 7 and kind of find that number. These are typically lowercase letters. The matrix itself will be an uppercase letter. So like this may be matrix A, in which case the lowercase letters will all be little lowercase a's. If we had some other matrix B, it would likely call its elements B11, B12, etc. The little lowercase letters usually are the same letter as the matrix, but lowercase, referring to single numbers, uppercase referring to the entire matrix. Okay, and so you want to be able to kind of figure out, we're talking about A73, go down to row 7, across to column 3, and it's that numbers that we're talking about. A few people have asked, what if you see something like, you have a big matrix and it's like A117? And you're like, is that 11th row, 7th column, 1st row, 17th column? What's happening there? Typically, they'll either exaggerate the space between the two numbers or just add a comma. If you start getting into the double digits of rows or columns, we don't really do that very much. I mean, we'll be dealing with much smaller matrices for the most part. So I wouldn't anticipate that as a problem, but obviously, yes. In big problems, you could end up with lots of numbers. You just generally put a little comma to separate. Yeah. That's just saying continuing the pattern. So the dots are just saying 1, 2, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, all the way to 1n, however many columns there are. And then this would say 1, 1, 2, 1, 3, 1, whatever, continuing that same thing. This is also along the diagonal, just continuing that pattern that will have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Yeah, it's just kind of saying it'll continue that pattern. That's what you do a lot of times if it's a big matrix, or if you just kind of, this one we don't have a specific size.
So if it was like 8, 11, 11, it would be just spaced out?
It'd be spaced out or you'd add a comma. Different people that do it different ways. But yeah, if you have more than 2 digits, you'll usually stick in a comma or a well-defined space to show which one you mean. But again, yeah, we won't really do that very much. Okay, identity matrix. is a square. Square matrix. Square matrix means same rows, same number of rows and columns. So whenever you talk about a square matrix, M and N are the same, meaning 3 by 3, 4 by 4, 5 by 5. Okay, one's along the main diagonal. The main diagonal starts in the upper left and ends in the lower right. So we talk about the main diagonal from the upper left to the lower right-hand side of the matrix. In an identity, all of them are ones. Everything else is zeros. Okay, so like A11, A22, A33, A44, those are ones. So that's what this means by when I is equal to J. Everywhere else, you'll have zeros. So like A12, A21, A34, A45, whatever. When I and J are not the same, you'll have zeros. So you'll have things like 1001 or 100010001. Okay, or whatever. Okay, you could make it as large as you need to. Those are called the identity matrix. It's the multiplicative identity in matrix multiplication. It acts like the number 1. Okay, so like when 5 times 1 is 5. Well, here A times the identity is just going to give you A. Or the identity times A will give you A. Okay, it's the identity, meaning when I multiply, nothing changes. Just be careful because order in multiplication matters. It's like if A was 2 by 3, this is still true, but you wouldn't use the same identity in both, right? To make this work, I would have to use the 3 by 3 identity from the right or the 2 by 2 identity from the left. It's still the identity, doesn't really matter. Just make sure you're paying attention to that, the idea that those inner dimensions have to matter in the multiplication, which means order matters. Okay, when you're doing multiplication, which we'll see quite a bit later as we start doing more matrix multiplication. All right, so multiplying matrices, I think we briefly mentioned this yesterday. It's just dot products of rows of the first one with columns of the second. So you don't always have to do it on paper, like write it out, but just make sure that when you're multiplying, those inner dimensions have to be the same. If they're not, you can't do the multiplication. Several of the problem set problems, oh, I think I added this one from the one that's online if you printed it. Several of the problems on the problem set don't match. You can't do it. So that's literally would be your answer. You can't do the multiplication. So double check that before you do anything. You don't have to write it down 2 by 2, 2 by 3. Just make sure the inner dimensions match. The outer dimensions, especially in larger, more varied matrices, can be helpful because you know what I'm looking for is a 2 by 3 matrix. Mm-hmm. So those outer ones are helpful. Usually when you're like in 2s and 3s, it's not very hard to figure that out. But if you have large matrices with different shapes, it can be like, well, what numbers am I looking for here? So this one should end up being 2 by 3. And literally you could do it in any order you want. Okay, like you could go, let's go for this number here. Okay, that is A2. Well, let me choose one that's not got the same number twice. That's A2, 1. Okay, and you could go out of order. Typically, there's not really much of a reason to do that. This is just row 2 from the first matrix, 3, 5. Column 1 of the second matrix, 1, 3, and you're taking a dot product. Okay, so I'll have 3 plus 15 is 18. But generally we would just go in order, right? I would start in the first spot. That's row 1 and column 1. So I kind of just go across and I'm like doing these little dot products of row 1 and column 1. So I'll have 2 times 1 and -1 times 3. So that's 2 minus 3 is -1. And then I'll just move across. Next spot, I'm still in the first row. But now I'm going to look at the second column. And I'll have 2 times 0 and -1 times 1 is -1. Yeah, sorry.
Wouldn't that spot be 2, 3, not 2, 1?
Yes.
2, 3. Yes, absolutely.
That's column 3.
Yes, 2, 3. Thank you. And was that you too, Zainab?
Yeah.
Yeah, that should have been 2, 3. So this should have been a -1, 3. And so this should have been -3 and 15. Yeah. Yes, and make sure you point that out because it is very easy to make mistakes on matrix multiplication. It's a bunch of little arithmetics over and over and over. So make sure you point out, like, did I do those two right? 2 and -3 and then 0 and negative. I think I did. Okay, and then as I move across, again, I'm going to take row 1, column 3. I have -2 and -3 is -5. And then when I move down to the next row, that's when I'll start using row 2 of the first matrix. So row 2 in column 1 is 3. That one, oh, that's the one I accidentally did before. That's the 18. And then row 2, column 2 is 0 and 5. Okay, it's very easy to make little arithmetic mistakes. You're doing all these little adding, a bunch of little numbers. Even if like a negative is off in one element, sometimes that can make the whole answer, like once you finish doing the problem, look totally wrong. So make sure you show some in-between steps. Because if I can tell like, oh, look, you just added wrong, or like what I did, you just did one element out of place. That's not a big deal compared to like if you don't know what you're doing at all and you're just like making stuff up. So make sure you show some in-between steps. This will obviously not be the last step in linear algebra, is like one multiplication. You'll do something with that matrix. Make sure you show those steps so that I can see, oh, look, you just left off a negative here, or you accidentally said 2 plus 3 was 6 instead of 5. Well, that could throw your answer off by actually a lot, making those little mistakes. But if I can see it's a little mistake, not a big deal. But I have to be able to find that. So make sure you kind of show in between steps and things. Okay, multiplying by the identity shouldn't change anything. You could verify it by actually multiplying. All right, if I take row 1, 0 times column 2, 3, 2 times 1 and 0 times 3 is 2. And then row 2 times column 1, 0 times 2 and 1 times 3 is 3. So we see nothing has changed. What we'll start looking at tomorrow as we start to actually solve some systems of equations is the identity is often a good place to start in what I'm needing to do, because I can kind of manipulate the identity and predict what the outcome will be. So for example, here, if I switch the rows of the identity, I know the multiplication will also switch the rows of what I'm multiplying by. So notice that second one is the identity, but with the rows switched. When I multiply, it will switch the rows of the vector 4, 5, right? 0 times 4 and 1 times 5 is 5. And then 1 times 4 and 0 times 5 will give me my 4. So I can start taking the identity matrix and manipulating that a little bit to cause changes that I'm wanting to occur in a problem as I'm trying to solve a problem. But again, we're not going to solve quite yet. So a huge point of linear algebra, the vast majority of the course is devoted to solving systems of linear equations. We'll do a lot of examples, 2 by 2, 3 by 3. 2 equations, 2 unknowns, 3 equations, 3 unknowns. It applies to all sorts of sizes. Again, generally as they get bigger, they don't get more difficult, they just get more time consuming. So if you can do it with 2 or 3, you can do it with 10. It's just going to take you a long time and a lot of paper. But it's the same, like a bunch of little adding and multiplying and adding and multiplying and adding and multiplying, not any more difficult of math. Okay, so generally when we talk about solving a system, we're saying we want to find an x, a y, and a z that makes all of our equations true. So in this case, all 3 of these equations true. Okay, sometimes it exists, sometimes it doesn't. Sometimes there's one, sometimes there's many. And when we say many, we mean infinitely many. Typically, when we have 3 equations, 3 unknowns, we want 3 equations. Okay, if you have 3 unknowns and only 2 equations, you're usually not going to have enough information to find just one solution. Okay, if you have 3 unknowns and 4 or 5 equations, you're increasing your likelihood that there are no solutions. So typically, you're kind of wanting 3 unknowns, 3 equations, and you can often find then the one solution. That's usually what we're looking for, the one. None is usually not good. Many is usually not useful. We want there to be that one specific unique solution, and that's usually what we're looking for. So with 3x3s, we can picture these as planes, right? So visualize you've got 3 planes and the different ways those planes can intersect or not intersect. Okay, you have 3 main options. You have no solutions. Okay, so if we were to graph these 3 planes and we saw 3 parallel planes, we would know there's nowhere then that all 3 planes will meet if none of them meet. You don't even have to graph them. You should be able to tell that pretty quickly if the coefficients are multiples of each other. Okay, that's going to cause parallel planes. So if you have a plane like x plus y plus z equals 1, and 2x plus 2y plus 2z equals 1, and 3x plus 3y plus 3z equals 1, or whatever, just the coefficients are multiples, that's going to indicate parallel planes. Okay, you also could have no solutions if you have 2 parallel and 1 that's not. Right, 2 parallel planes, then 1 that's not. Think like the ceiling, the floor, and a wall. The ceiling and the floor are parallel. The wall is not. The wall touches the ceiling and the wall touches the floor at some point, but it doesn't ever all 3 touch at the same time. Okay, so if even 2 of them are parallel, but 1 is not, you're going to end up with a situation where there's not one intersection for all 3 planes. And then the other one, think of like a tent. Okay, if your planes kind of do that, then they all intersect each other, but they're never all intersecting in the same location. Okay, plane 1 and 2 intersect, 2 and 3, 3 and 4. 1 and 2, 2 and 3, and 1 and 3 all intersect, but never in the same place. So that's another possible one. That's the hardest one to identify because they won't be parallel. So you're not really going to like instantly see those parallel coefficients that are happening there. Okay, we could end up with infinite solutions. One being, you have the same plane. Okay, if I take any of those equations and multiply the entire equation by something, I will get a new equation, but it will describe the same plane. So if I had like x plus y plus z equals 1, and 2x plus 2y plus 2z equals 2, and 3x plus 3y plus 3z equals 3, 3 equations, 1 plane, meaning they intersect everywhere because they are the same plane 3 different times. You could also have them intersect in a line. Okay, so think if 2 planes intersect, they intersect at a line. A third plane could go through that same line, in which case they don't intersect in one place, they intersect in every single location on that entire line. Okay, so you kind of have a situation where your planes are kind of doing this. Picture those are planes, not lines, but they're intersecting in a line there. So you have two intersecting in a line, and then the third one goes through that same line. And then you could have 1, which again is the main thing. There's 1 point. That's usually the thing we want to occur, is what thing do I want to do to maximize revenue, minimize costs, whatever it is that you're trying to do in your problem that you're solving. You want that solution. You don't want none. That's not good. You generally don't want infinitely many, because it's like, well, what do I do then? You usually want this kind of like, this is the way you want to maximize or minimize something or whatever you're trying to do. Okay, meet these 3 conditions. Okay, we can solve this using matrices. Again, when you're doing them with 2 by 2 or 3 by 3, you might say, why would I use a matrix when I can use algebra 1? Okay, I can use elimination, I can use substitution, and I can do this the same way. The reason we developed this with matrices is it's not a guess and check thing. We can have a specific method that will work, and it will work for 12 equations with 12 unknowns. Where if you start trying to do algebra 1 methods with 12 equations and 12 unknowns, you're likely going to get really lost in what's happening. Your work will get really messy. It'll be hard to follow what's going on. Matrices create a really algorithmic, organized way of solving that kind of scales up to any size really well. So yes, in small ones, it's not really that much more useful. The larger they get, the better they are. So that's kind of why we go towards using those matrices. So first thing we do is we write the coefficient matrix. Coefficient matrix is just a matrix with the coefficients of the equations in it. Before doing it, make sure your equations, you've lined up the x's, the y's, and the z's. And generally, I would say you solve to get the variables on one side and everything without a variable on the other. So that when we go to write the coefficient matrix, you just look across each equation. My coefficients in the first one are 1x, 2y, 3z. So I'll have a 1, a 2, and a 3. 2x, 5y, 2z. So that's 2, 5, 2. And then 6x, negative 3y, and 1z. So I'll have 6, negative 3, 1. Okay, this is called the coefficient matrix. We often have it labeled as an A, but it doesn't have to be an A. It can be capital letters is usually what we use. So each column represents the coefficients of one of the variables. So like column 1 here is the x's, column 2 is the y's, column 3 is the z's. So make sure you've lined them up. You don't want to just do random coefficients. All the variables need to kind of be grouped into a column. So if your equations are mixed up, I would then do it. And then this is equation 1. The rows represent the different equations. The columns represent the different variables. And so if I added equations, it would add rows. If I added variables, it would add columns. Okay, and so we'll use the coefficient matrix. And we can take any number of equations and write out then one matrix equation. So it's our coefficient matrix. And then we'll put a vector that just has our unknowns, our variables in it. So in this case, x, y, and z. Just pay attention. It's not always x, y, and z. It could be a, b, and c. It could be x1, x2, x3, whatever. And then that should give us a vector 6, 4, 2. Okay, and so we have this one matrix equation. If you had 10 variables, 10 unknowns, 10 variables, 10 equations, you would have still one matrix that was a 10 by 10 matrix times a vector with 10 elements equals a vector with 10 elements. So we usually write this as ax equals b. And so that's literally the equation we will be dealing with for the majority of the semester. Is ax equals b. A being the coefficients, x being a vector with a column vector with the variables in it, and b being a column vector with the scalars, the stuff you put on the other side of the equation in it. Order matters. So don't switch and think it's still going to work. Okay, you can't do X times A equals B, and that's not going to really work out. So make sure it's kind of got to stay in order. Matrices, that's the downside of multiplication. You can't switch order. So when we say A is the coefficients, X is the variables, B is the numbers, it kind of needs to stay in that order. Okay, and so this is just, think if you just took dot products, you're going to get your original equations back. Row 1 times column 1 will give you your X plus 2Y plus 3Z. That should equal this first element, 6. Then if I were to do the next one, row 2 times that column should give me 2X plus 5Y plus 2Z, and that should equal what's in this second element here. So if I were to just do my dot products, I'll get my 3 equations back. So this is equivalent, same thing. Okay, so writing it in this form, we're not really changing anything. We're just changing the way we're going to kind of address this. All right. So we're pretty much going to end there. I'm going to do one more kind of example. We're not going to solve anything today. We're just kind of setting it up. Tomorrow, we'll start doing some of the different methods that you could use for solving these systems of equations. For now, again, we're just kind of going to look at putting them from a bunch of equations into this matrix equation and try to avoid thinking, well, I can just solve it. This is super easy with algebra 1 to solve. True. Okay, this one should be really easy and you should be able to do it pretty quickly, solve this system of equations. But for now, we're using these really easy ones to develop the method that would work on the much harder ones. So you're just kind of practicing putting the system of equations into a matrix equation here. If you multiply it out, you should get your system of equations back if you did it correctly. And again, this is the same as a linear combination of column vectors. So we put it all into a matrix, but if you look at each matrix of each column of that matrix, they're the coefficients of one of the variables. So you could look at this also as just X times the column 3, 1 plus Y times the column negative 1, 1 equals 3, 5. Right? We could break up that matrix equation into each column times a vector. Times a variable. It's the same thing, right? When I do multiply this, the 3 will be times an X and the 1 will be times an X and the negative 1 will be times a Y and the 1 will be times a Y when I go to do my dot products. So I could write it in this way as well. And again, that's just more practicing this idea of linear combinations because that'll come up later. Yeah, Xander.
In that test, will you ever say you have to write it in that linear combination?
Possibly.
Okay.
Okay, so that's all I've got. If you guys have questions, I'm happy to answer those. If not, then you guys have a good day and I'll see you guys tomorrow.
Can you post it this afternoon?
Bye,
Yeah.
thank you.
Thanks.